earned scholarships for students at UWR. So he gives back as well as being a very nice man. So here you are, Bill. It's all yours.
Thank you very much. Well, I appreciate this so much for having me here. Let's not get upside down. There we go. So we're going to be talking about geologic time. And well, first thing I want to do is just thank you for inviting me on Easter Sunday and electing to spend some of this special day with you. But we're going to be talking about the planet Earth through time. And this picture suggests that our planet has changed quite a bit, going through lots and lots of different phases through its history to give us the really wonderful, resourceful planet that we so love today. And that history has gone on over 4.6 billion years of geological time. Well, a lot of people have trouble sort of understanding how long that is. So if I did one slide for each year and showed it at one slide per second, this show would run about 4.6 billion seconds, which amounts to 147 years. So since I only have about 25 minutes, I think I better sort of get on with that. Now it's sort of hard to really grasp that period of time. So one of the things I did just out of sort of inspiration, so I took my King James Version of the Bible and tried to scale it out. If this actually told the story of 4.6 billion years, each one of these pages would represent just over 4 million years of time. Just to show you just how many years that is. It's really sort of amazing to think about that as spanning Earth history. So I'm going to kind of use this as a prop to give you an idea for sequencing and how these things basically happen. Well, if we go to in the beginning, which if I skip all this introductory stuff, is page 1, Genesis, in the beginning we had, for our planet at least, and of course the universe is billions of years older than this, for our beginning was about 4.6 billion years ago, when if you went back there you would see basically a dust cloud, a nebula, that got disturbed by something, maybe an exploding supernova nearby, or some event that caused it to start to collapse and collapse into planets and masses. And little particles collided together to make bigger particles, and they collided to make bigger and bigger and bigger particles as time went on. And the body that formed this planet-sized mass really didn't look a whole lot like the Earth today. In fact, we call it the Proto-Earth, and here's a sort of a little sketch of it with bodies coming in and impacting and colliding and making it get bigger and bigger. And of course, the bigger it was, the more gravity it had to pull in more stuff. So planets have a tendency to kind of grow over time. But early on, there was a very big impact. Another one of these protoplanets collided with the Earth, and the two bodies merged, but a whole lot of material was broken loose and became our moon. So the moon formed very early, and terrestrial planets having a moon the size of ours is very unique. And this is a pretty unique event, and our moon helped stabilize, serve as an anchor for our planet over the centuries, and also provided us with tides. And tides are very important in the development of life in the shallow seas. So the fact we had a moon is really pretty central to what happened later as life developed. Well, these collisions and also the presence of radioactive material that was clumping together eventually caused the Earth to melt. And this allowed the denser materials to sort themselves out by sinking basically to the center of this ball, and the less dense material migrated more or less toward the outside. This event occurred approximately 4.5 billion years ago. So it actually gets us into Exodus here, page 88, which is about the time the golden calf was being around. So that much time had passed, comparatively speaking, since the solar nebula began to condense. But the effect of that was a beautifully layered planet like we see today, with the atmosphere, the hydrosphere, the crust, the mantle, and the core. Our planet has a particularly large core because it was the core basically of two fairly large planetoids that had collided together. So this very, very large core is also fairly unique for terrestrial planets. And it's very important to us because the outer part is liquid, and there are currents of this molten iron and other metals circulating around, which produces a magnetic field which extends way out into space, and this magnetic field protects us from a lot of the cosmic rays and radiation and other particles coming in, either diverting them away or funneling on into the polar regions. So the fact that we have a core, a uniquely large core, is also going to be very important to us later on in the game. Well, soon after the planet had cooled down, we had an atmosphere, we had a hydrosphere, and life appeared within these seas. Now, we don't have a lot of evidence for exactly when life developed. We have some what are apparently fossils of microorganisms in the rocks from about 3.8 billion years ago, which takes us up into Deuteronomy, about in here. These were photosynthesizers. So what they were doing was they were taking the abundant CO2 in the atmosphere and converting it into oxygen, which was a waste product for them anyways. And we'll see the effects of that as we go down the line a little bit. Now I'm going to try and key this talk into rock layers that we have around here. We don't have many rock layers that go back this far that have evidence of life in them. The oldest rocks we have in our area is a metamorphic rock called gneiss, which is a very beautiful rock, and you see this all around the Twin Cities where it's quarried over in the Minnesota River Valley. These rocks have been deformed by being involved in mountain building and deep burial and faulting and all sorts of stuff. So we don't see much evidence of the living organisms that might have been around it in a lot of these rocks. We were fortunate, at least in a few places, that rocks this old have not been so thoroughly reconstituted. Well, you remember these photosynthesizers making oxygen in the atmosphere. Initially, this oxygen was tied up by uniting with other elements and precipitating out as solid minerals. But by the time we got to about 2.2 billion years ago, which gets us up into the Psalms, about the age of 533 or so, right up in here, there was enough oxygen being produced that we had free oxygen actually in the atmosphere. So we were producing an atmosphere that you or I could actually go back and breathe. We went back further than this. We just dropped dead because there's no oxygen to breathe. So this event is called the Great Oxidation Event. And it lasted for quite a while, but once we had oxygen in the atmosphere, the oxygen could produce some ozone, and we had an ozone layer, which is another layer of protection for living organisms. Before this time, the UV radiation would have basically destroyed more complex cell development, certainly anything on the land, and certainly in the upper parts of the ocean. So it's very important for us to have an ozone layer at some point for life to develop to more complex forms. Another aspect of this was that as the oxygen became more abundant, it changed the chemistry of the ocean. The ocean initially had a fair amount of iron dissolved in it, which we don't see much of that today. But this iron was starting to unite with the oxygen and basically cleanse the ocean of iron, leaving big deposits of iron-rich sediments on the seafloor, which we call banded iron formations. These are beautifully developed in lots of parts of the world, but particularly in the Midwest, for Minnesota, you can see these rock layers. This is up into the Tower Sudan area. We have them in Wisconsin and basically worldwide. And of course, this is where the Iron Ranges got their ores. This is the remains of that great oxidation event left behind in the sedimentary record. Well, early on, the Earth started to develop what we call plates, these big masses of the upper part of the Earth colliding around and moving around at each other. This produces the world's big mountain ranges. The process is still going on today. And our period of mountain building here in Wisconsin took place about 1.8 billion years ago, 1,800 billion. That gets us up to Isaiah here in the text. And if you come back here at this point, you would see a very large mountain range through our region, and it's now largely eroded away. But the effects of that are all around us. If you look at some rock quarries in the northern part of the state, you see sedimentary rocks that have been tilted nearly vertical. In other places, we see remains of the seafloor, oceanic rocks being tilted up, again, nearly vertical, as this was exposed in the copper mine that was active in the Ladysmith area back in the 1990s. A lot of granites also formed during mountain building, and many of the granitic rocks that you see being cut through by rivers along the rapids and beautiful waterfalls in the middle of our state are products of granites that form in the cores of this very old mountain range. Well, mountain building in our area basically started to wane once we get to about 1.6 billion years ago, and that gets us up to the interesting page of 666 in our text. And about that time, we were having sandstone being deposited around here, which got a little bit metamorphosed to become a rock called the Baraboo quartzite. Here exposed, incidentally, along Devil's Lake, which is also kind of interesting. But if you go down there and hike around the bluffs, you're hiking through these old sand deposits. So that gets us to about about in here in my King James Bible. So a fair amount of time has gone by. You can see the same quartzites if you go to another important Wisconsin tourist spot, which is the Rib Mountain. You're climbing up on a big mass of quartzite, beautifully exposed there. And this was quartzite that had been caught up in a fairly large mass of granite, which came in as magma. If you get to the top of Rib Mountain, climb up on the observation platform and look around, you'll see all these quarries in the lowland that were this granitic rock. And so our granites formed at about this time, a little younger than that, about the time we're about up to Jeremiah now, page 700, it's about here. This granite, some people locally call it rotten granite, which is kind of a strange thing, but it's been weathered now, so it's very granular. So when you have one of these weathered outcrops, you can stick your hand to the granite and actually crumble it in your hands. It's like they're very convenient for making gravel and stuff, and that's what a lot of these quarries are working, is this one here, which is just south of Rib Mountain. But if you go below the weathering zone, this granite also makes beautiful building stone. In our state rock, the red granite is from this particular time. And it's a lovely rock which you can recognize if you see this used on buildings and other places. Now, about 1 billion years ago, we get to Hosea, where we were about 779. So, yeah, about right here. So we've come a fair amount of way through this. Our continent was being rifted apart in this area, being basically pulled apart. A basin formed, and lava and sedimentary rocks were filling that up. This rift zone extends way down to the south, actually traceable all the way to Oklahoma, then up through the Great Lakes area, and then down through Michigan. Much of that is covered under younger rocks until we get about to St. Croix Falls. And from then on, all the way around Lake Superior, you can see many remnants of this volcanic belt. So a good place to see this is the trips up to Interstate Park, some nice sunny day, and hike around, and you're on these old lava flows from this particular event. Well, eventually, we got to the point where life was becoming abundant in the earth. We passed an event that geologists call the Great Cambrian Explosion. This happened about 550 million years ago, and the rocks in our area from that time were deposited. They're a little younger than that. But at that time, we have abundant evidence in the rock of complex life having developed on our planet, and life that discovered how to make shells and bones and teeth, which are preserved much better than the soft parts. So once we get to the Cambrian, we start seeing really detailed information on how the Earth's ecosystems have developed over through time. In our part of the world, we had a shallow sea then spreading back and forth. It would recede some time and spread back in and so forth, and would leave wonderful sedimentary rocks. A lot of those are sandstones that represent beach sands and shallow off-water sands like we see here. This is down in Florida, but this is what this area would have looked like back at that period of time. And we see those rocks exposed when the rivers cut deeply enough through them. This is at Boom Hollow near Stillwater. It's a great place to go and look at the sands deposited by these seas, and lots of other places around. Sometimes the seas were leaving more chemical sediments. This is some of the fossils in the sandstone. You see those white fragments there are phosphate shellfish fragments. And so you don't need to be an expert to recognize you're looking at fossils when you start to see these abundantly in these rocks. At other places, the sea left chemical sediments like limestones and a relative called dolostones. And we see those in the beautiful bluffs that line the Mississippi River and many of our river valleys around here, including the Kinnickinnic Valley. If you go to there he is again, the Devil's Punch Bowl in Kinnickinnic State Park, you can just roam around these beautiful carbonate rocks. And if you look carefully, you find structures in the rock that looks like cabbage heads that have been cut through. These are called stromatolites. They are produced by a type of bacteria, cyanobacteria, which lived in colonies. And they would bond calcium carbonate from seawater together and make these mounds, layer after layer after layer, perhaps representing different seasons. And you can find a number of these if you look carefully at the rocks. You see these layered structures in there. Now, because these are photosynthesizers, this also tells us that this, how do geologists know this wasn't deep water? Well, for these to grow, the sunlight needed to be able to get to the bottom, so they can't have been very deep water. There's all these little indicators in the rocks that allow us to reconstruct what this area was like. And look for modern examples. For stromatolites, one of the best places to go is over in Western Australia, where we could see an environment very much like what this area looked like when those bluffs were being deposited. Shallow seawater, there's mounds of stromatolites growing up from the bottom. So stromatolites are survivors. They've been around for a long time and allow us to understand what we see in the rocks here. Where our bedrock around here formed soon after that, we have the sandstones called the St. Peter Formation, which you probably maybe have driven through the road cuts and the bypass a number of times and seen these. And on top of that is another lime layer, again produces the seas went in and out, and that's called the Platteville Formation. The Platteville is also really full of fossils. There are wonderful fossils you can find in there. You pick up slabs of this rock and turn them over. There are shellfish and all kinds of wonderful things that allow us to reconstruct the complex ecosystem we have. And this is an artist's conception of what things would look like at about that time. When we had snails and trilobites, we had these big squid-like things, which are called cephalopods, producing shells that are at times 10 feet long. There are sea lilies and all kinds of stuff, showing how complex the ecosystem was at the time the rocks around here were being deposited. But at that time, all the complexity was in the ocean, so life didn't move on to land until about 300 million years ago, which gets us into St. John here, about 922, so no, 926, rather, it's about right there. We don't have rocks from those ages exposed in our area, but they are exposed further south in Iowa and Illinois and Indiana and so forth, so we have a pretty good record for what things were like about that time. But we're having another event rather similar, at a very similar time. If we go back to about 270 million years ago, we're back in the Romans, we come up to the Romans, and we had fluids bearing metals coming into our limey rocks and leaving behind some pretty large ore deposits, primarily lead and zinc deposits. So if we went back to the early 20th century or so, we would see many active mines around the Platteville area and Mineral Point and all those areas, Dodgeville and so forth, that was exploiting these deposits. We got our state mascot from there, the badger, refers to these miners who would spend a lot of time underground in their narrow little holes and come up sort of dirty and scruffy and ill-tempered, and so it's not look like badgers. But then this is one of the mine crews from about 1900. We also have our state mineral was forming then, Galena, which is lead sulfide. We're not real fond of lead ore or lead in anything these days, but it's a pretty mineral, but we don't have much use for it. It's one of the reasons the mines were closing down, is the demand for lead, fortunately, was declining as we found other uses for paint and gasoline and all sorts of stuff because of the problems we were finding with health effects of lead. But you can't blame the mineral. It's a nice thing. You can handle it, and it won't pollute you too bad. It has our state mineral commemorating the mining that took place at those times. Well, dinosaurs did appear. They appeared in the 1 Corinthians. No, they didn't. About 230 million years ago. So we have to back here. We got this. Yeah, there we are. About there, 1 Corinthians. And I don't know. Everybody seems to love dinosaurs. Kids love dinosaurs. And I got interested in geology because I was nuts for dinosaurs, which was fine. And they were around for quite a while, but eventually they became extinct about 66 million years ago. Now, we don't have fossils of dinosaurs in Wisconsin that we know of because Wisconsin was primarily above sea level all through that time, which is not conducive for sediments being deposited and preserved. They erode away. But there was a seaway that went through western Minnesota and a lot of the central U.S., and if you go to the right place, you can actually find shark's teeth and other fossils from this period of time there. Eventually, extinction took out the dinosaurs, and so 66 million years, that was about Titus. It probably didn't quite look like that, okay? That's not actually, it did, so we're about here. So we're moving along. What it actually looked like was an impact of a fairly large meteor about the size of Manhattan Island, which came down and collided with our planet about the Yucatan Peninsula. And this created a mass extinction in which we lost many, many of the species. But it gave an opportunity for the survivors to come back and repopulate the globe. Now, mass extinctions like this have happened through geological time. There's about 5 or 6 that we know of. Some of them are tied to extraterrestrial impacts. But we have a friend that keeps us from getting a lot more of these impacts, and that friend is out in the outer solar system is Jupiter. When an asteroid gets into an unstable orbit, most of the time it runs into one of the gas giants, especially Jupiter. So they don't come around our way and collide with our planet that frequently with such catastrophic effects. We can get smaller ones that will come in much more frequently, but the big, what are called planet killers, are fairly rare in our solar system because of the structure we have and the effect that Jupiter has on us. So we're very, very fortunate for that regard. But anyhow, this set the stage for mammals to come along and succeed, and human beings came along about 2.8 million years ago, if I believe my archaeologist friends, which actually gets us pretty much to the last page of the Bible, to Revelations. So we're already to the very, very last page here before human beings appear on the scene. They probably didn't look quite like that either. Well, they didn't have an easy time of it because they came in just in time to get into one of the Earth's periodic ice ages, where for about 2 million years the ice would expand and contract around a lot of the land masses of our planet. I think it's no accident that human beings did well early in Africa, which saw very few effects of these glacial periods. We had a lot of glaciation up in our part of the world, as you know, and the ice carving a lot of the landscapes and leaving behind a lot of the sediments behind, as we can see here. But it finally receded about 12,000 years ago is when it left the St. Croix Valley area. So not all that long ago. In fact, if we look at the Bible here, we're actually on the very last page when the ice was receding, the very last page of Revelations. Now, today being, and then a bunch of the debris left, as you can see. If you go out and like to pick agates and stuff, you really love this stuff, glacial debris. So Jesus was born, if we believe historians, about sometime between 3 and 6 AD. And if we look at the Bible here, that accounts for the last 6 words of Revelation. Interestingly enough, which are the words, Christ be with you all, amen. Which is pretty interesting in that regard. And at the end of all that, we have our beautiful world, Gaia. And we can see, though, that the life we have on it is really a beneficiary of the fact we have a really big core. We have a wonderful moon that helps us out. We have Jupiter that helps us out. We have a sun that's been very stable over a long period of time, and so forth. A lot of nice things have happened, which has protected our planet from a lot of more catastrophic things to happen. Now, is this unique? Well, we have the tools to go out and find planets that are around other solar systems, and we found thousands of them. Some of them are very close to size and character to our planet. We don't have any details yet, and they're very far away. So, the fantasy of actually being able to go out there and live on them, it's really a long ways away for us. So we might say, well, maybe the Earth isn't really all that unique if there are thousands of Earth-like planets out in the galaxy. But I will tell you this, I believe it is very unique. Just consider the history that we've had here. Microbial life appeared soon after the planet had an atmosphere and an ocean. And there's a good chance that microbial life is probably quite common. It seemed to have come up almost immediately. And we may have other microbial life on some of the icy moons, or maybe we had some develop on Mars and so forth. But now, complex life, when did that appear? That took a long time to appear. In fact, we have the first record of really complex life in the rock record after 4 billion years of history had formed, about 500 million years ago. So we're 80% through Earth history, a history where the planet has been very stable, in a very nice atmosphere, and complex life took billions of years to appear. And arguably intelligent life, if we count ourselves, took 4.5 billion years to develop, even under what we might consider cosmically optimal conditions. So my argument is that bacterial life is probably pretty common in the cosmos, but complex ecosystems, where you have organisms expand in every conceivable environment and interact with all these beautiful things, that would be one of the rarest things in the cosmos. Because it took a lot of things going right for that to develop here on our own planet. So we get to April, a day like today, beautiful sun is shining, things are beginning to wake up, we celebrate rejuvenation, we celebrate the coming of the spring, we celebrate Easter, we celebrate our planet and Earth Day and so forth. We might be celebrating something that maybe is one of the rarest things in the solar system, a complex ecosystem that has intelligent life. So to conclude, our own life here is one part of the very last period in the very last word of our Bible here, amen. And with that, I'll leave you and be glad to answer questions if you have any. So thank you again for